All right, lesson 5. We are skipping over lesson 4 just because our notebook has them mislabeled, so we're not going to worry about the labels. We're going to call this lesson 5. Lesson 5 focuses on exponential functions. In general, an exponential function has the form where f of x is a to the power x. Really important. A is a positive constant. I'm going to add another restriction to this. A cannot be 1 because 1 to any power is just 1. So that is not an exponential function. But anything other than 1, as long as it is positive, we call this an exponential function. For an exponential function, the variable is always the exponent. So this is not the same thing, does not equal x to the power a. That's different. That would be a polynomial function, right? A reminder of some of our exponent laws: anything to the power 0 equals 1. Anything to a negative power ends up being the reciprocal. And if you have a fraction in the exponent, the top or numerator is the power, and the denominator is the root. If you have a base that is between 0 and 1, such as 0.5, we did this in one of our previous lessons. Our key point when x is 0, y is 1, because anything to the power 0 is 1. So we end up with our key point here. As x gets larger, though, this is going to get smaller, so we get closer and closer to 0. As x gets large, but in the negative direction, so like -5, -10, -100, we end up with an exponential that looks like this. And this is what we call exponential decay because we are getting smaller. Okay, so exponential decay is when the base is between 0 and 1. So this, let's call it B for the base, is between 0 and 1. Key point is this thing right here. Our exponential decay has the coordinate 0, 1 as our key point. Everything else, you can essentially use a table of values to plot some of the points that you might need, but 0, 1 is always going to show up. So here, the domain is all reals. Our range must be a positive number, and it's actually not, and it's going to be a strict inequality. We cannot touch the x-axis because there is nothing we can put in the exponent to make y equals 0. So we actually have a horizontal asymptote at y equals 0. We cannot ever touch that line. And finally, our intercept is at 0, 1. So these are key points of an exponential decay graph, and this pretty much applies to all of them because we've only done the one key point. Now, if our base is 1, 1 to the x, as I mentioned before, x could be 0, 1, 2, 3, negative 1, 2, 3. Doesn't really matter. We're going to end up with a horizontal line. This is the line y equals 1 because it doesn't matter what the x is. Not very interesting here. All right, if we have a base that is greater than 1, then we have exponential growth. And again, our key point here is going to be 0, 1, because that's when x is 0. And as x gets larger in the positive direction, we get really, really big. And as it gets large in the negative direction, we get very, very small. But again, we end up with a horizontal asymptote at y equals 0. And our domain and range essentially is the same as what we saw before with the same intercept. Okay, moving on. Couple of notes. All these graphs will go through 0, 1. If it is between 0 and 1, we are looking at a decreasing graph. So again, a decay graph. If it's greater than 1, it's a growth or an increasing graph. And if A is 1, then it's constant, and that's just not interesting at all. Okay, if the base is not 1, then here's our domain, all real numbers, and the range is greater than 0, just as we noted up here. As a quick reminder, things we should have learned and done almost every year since grade 9, at least at our school, these are the exponent laws. We're using these laws in order to help us rearrange some things to make life easier and to help us be able to graph our functions. So in example 1, why is this important? Let's take a look. Remember, we just finished talking about transformations. Let me rewrite this. Y equals -2 to the power x plus 3. Okay, first, let's graph y equals 2 to the x. We just did this on the previous page. We start at 0, 1, goes up this way, down this way. Now I have a reflection over the x-axis, and I have shifted the graph up 3 units. So 1, 2, 3, my intercept, 1, 2, 3, is going to be here. And I have reflected it over the x-axis. Ooh, Mrs. Gordon, what am I doing here? Let me do mapping notation. You'll see why I stopped what I was just saying. My x and y are now going to be transformed to x negative y plus 3. The reason I say that this is important, remember that when we do transformation, we follow the ERT rule. Expansions, reflections, then translations. So that was my error there. So I need to reflect it first. I don't have any expansions here. So I'm going to reflect it. So that's my reflection. Then I shift it up by 3. So my final graph will be 1, 2, 3, like this. Okay, now when I do reflections or expansions, my asymptotes are not affected. However, when I do translations, up, down, left, right, my asymptotes are affected. My original asymptote was at y equals 0. However, I've shifted everything up 3. So my new asymptote, 1, 2, 3, is at y equals 3. That's my new asymptote. So the black is the original, the green is when I did the reflection, and the pink is my final graph after I've done all the translations. So let's talk about what the new domain and range is. Looking here, my domain has been unaffected. So domain is still x reals. However, my range is now affected. I'm now going upside down and I've shifted my horizontal asymptote. So y is now less than 3 instead of greater than 0. And we're done. Let's take a look at example 2. Using the TI-83, compare the functions f to the 2 to the x and g is x squared. Which function grows more quickly when x is large? So let's take a look at our calculator here. I'm going to take a minute to open it up. What do we expect to happen? Oh, I can't even look at my screen. All right, let's give it a second to open up here. All right, so what I'm going to do is I'm going to put F into the Y1 spot and G into the Y2 spot. So let's go here, clear. I accidentally downloaded the French version of this, 2 to the power X. Oh, That didn't work. Let's try that again. 2 to the power of x. And then for the second one, I have x squared. And let's just double check our window. That's not going to be enough for us to be able to tell. So let's go from -10 to 20. And for the y's, let's go from -10 to 30, just so we get a better picture. And then I click on graph. Here we go. So that's my y1, that's 2 to the x. And that's my y2, x squared. Very difficult to see. So let's fix our window. Instead of going from -10, I'm going to go from 0. And let's bring it in. Let's do our max for the x's to 10. So from 0 to 10. All right, let's see if that crafts it better. So there is 2 to the x. And there is x squared. Which one grows more quickly? Essentially what I'm looking for is which one gets higher faster. You can see, maybe I'll zoom in one more time. Let's go to window. Let's go to the maximum. And let's make this, I don't know, 7 graph. So there is 2 to the x. And there is x squared. You can see after 1, 2, 3, 4, 5, at x equals 5, the 2 to the x is higher than x squared. So it grows more quickly. Let's write that down here. F of x grows more quickly. Quicker? Maybe that's some better English way of saying it. Grows quicker as x gets large. Both of them will end up going off to infinity as x gets larger. Another way of saying this is as x approaches infinity, f of x goes to infinity quicker than, than g of x. If we were to plot this like this is x squared, and this is 2 to the x. It goes up faster. All right, exponential functions occur in different types of applications. We're going to be looking at compound interest. You could look at population growth of bacteria, radioactive decay, all kinds of different things. And one of the things that we are going to look at is for financials, so compound interest, the equation is A representing the total amount equals P bracket 1 plus R over N to the power of N times T, where this is the original amount or the principal. R is the rate. T is the term, meaning how long are you investing it for, and N is the compounding period, meaning how often are they giving you the interest? Is it every month, every year, every day, every week? That is what the N represents. We're going to use this a few times. You don't need to memorize this formula. I'll usually give it to you if the question needs it. The other one that we talk about is exponential growth or decay. This is where we have, again, the amount of the population is P naught, meaning the original population. R is your rate, T is the time that that you are observing over capital T, which is the period of natural decay, or you can think of it as half-life or doubling life. So that's the other equation that we'll usually use when we do an application type question. I'm not going to do example 3 because we are not going to do regression for this section. So I'm going to skip right over to example 4, which is a half-life question. So I'm going to bring that equation back up. This is our half-life question, little t over capital T. All right, the question says the half-life of strontium 90 or 90 SR is 25 years. This is our half-life, capital T is 25. If the sample of strontium 90 has a mass of 24 grams, write an expression for the mass as a function of time that remains after T years. So remember that A represents the amount you're measuring and P represents the original amount that you have, which means I could write it like this. The mass I measure as a function of time equals the original mass I put in, bracket, half-life, so the rate at which I'm going to half, so 1 over 2, to the power of T over capital T. In this case, I can even substitute some of these numbers. I know that the original mass is 24. I'm expecting it to go down by half. They have not told me the time, so little t remains a t, and capital T is 25. So this is a function of mass that depends on time that will demonstrate the half-life of the strontium if my original sample is 24 mils, or 24 milligrams, sorry. So now in the next part it says find the mass. What is M after 40 years? So all I need to do is take that little t and substitute 40. So M after 40 years is 24 1 over 2 to the power of 40 over 25. I'm going to just chuck that into our calculator. So we go to the main screen, clear everything off. 24 times bracket. I'm going to write this as 0.5 or 1 over 2. It's the same thing. To the power of, and this is where we have to be careful with our exponents. We have to write this as a fraction exponent. So to the power of, make sure you have your exponents in bracket. I'm just going to double check I have the correct numbers in the right spot. There we go, hit enter. So we are going to have approximately 7.9 milligrams left after, sorry, yes, milligrams left after 40 years. All right, now this question is asking us to work backwards. Estimate the time required. So now I don't know T, but we want the sample to be reduced to 5 milligrams. What does that look like? Now I know my answer and I know my equation, 24 bracket 1 over 2 to the power of T over 25. This is where we have to remember some of our log rules. Okay, so I'm going to take 5, divide by 24. 5 over 24 equals 1 over 2 T over 25. Then I take the log of both sides. Log, I'm going to squeeze it in there. Okay, that gives me log of 5 over 24 equals T over 25 times log of 1/2. Remember that when we have an exponent in a logarithmic equation, it can be rewritten as the coefficient of that term. So I'm solving for T. So I'm going to divide by half a log, or not half a log, but log of 1/2 on both sides. So then I'm going to have, bear with me, I know it looks a little bit ugly and scary, but it really, really isn't, because our calculators are very powerful. T over 25. Oops, 25, not 24. Okay, and my last step is to multiply both sides by 25. Times by 25, and that's going to give me T. So I'm going to write exactly what I see there into my calculator. 25 times log 5 divide 24, close bracket, divided by log of 1 divided by 2, close bracket, equals 56.6. So the time it would take to start with 24 milligrams and to end with only 5 milligrams is going to be 56.6 years. If you are a little bit rusty and don't remember how to work with logs and exponentials, I have posted a Delta Math practice assignment that has lots of those questions for you to practice, going both ways, solving logs and solving exponentials. All right.